So now we're going to build a quadrotor simulation using MATLAB. Regarding this final project, I prefer you to use Simulink, but for those who are not familiar with how to use this Simulink, I'm going to program this quadrotor simulator using MATLAB. So if you are not able to get the proper license, then I suggest you to use Octave as a substitute. Okay, so let's get started. So let's make a new folder first. Let's say AE450. And inside of this workspace, I'm gonna build a new script. Let's name it as main. Right, CLC clear, and we're gonna build another path called a library. Okay. Sorry, I'm just gonna increase this font size. Much better, right? Okay. And let's define some variables like actually constants and this converters like radians to degree, 180 divided by pi, or degree to radian. Okay. And let's begin with initializing our parameters regarding the drone. Let's say drone number 1. We have a mass and arm length. Well, actually I'm using this side note, this PDF file that I uploaded to a KLMS. So here I have already covered a whole bunch of variables, parameters regarding our drone. You can see this constants and coefficients also, right? So here I'm gonna use this mass, arm lengths, and inertias, etc. From this lecture note. Okay. So we have IXX, IYY, and IZZ, right? And this values is nothing but 1.25, 0.265, 0.0232. Same for the IYY and IGG 468, right? Well, this is nothing but a dictionary in Python, right? So I just set all the parameters using the containers, and we can define our initial state based on this lecture note again. Here you see our drone. Actually, sorry. Our drone is actually starting from this initial point, this local NED frame, origin of the local NED frame. Okay, so I'll just put our drone first at 0, 0, 0, which is nothing but a x, y, g position, and then 0, 0, 0 again, which is our velocities, and then we use 3 Euler angles, right? Sorry. This is nothing but our Euler angles, which is pi, theta, psi, and finally this angular rates. Okay, I'm sorry. This is your PQR, right? And keep in mind that I just put a transpose sign here because it is nothing but a vector, right? So as we have done in the section 2.1, we defined our state variables as this inertial position xyz and velocities, our attitude as Euler angles, and PQR, nothing but angular rates, right? And also we have these control variables, right? So I'm gonna define our initial input vector as 0, 0, 0, 0. This is nothing but a, U1, U2, U3, U4. In our case, T sigma and M1, M2, and M3. Now I'm going to define our drone body. Okay, this can be seen from section. Actually, it's in nomenclature. Here we have our drone configuration, right? I'm gonna define our bodies with respect to the body frame here. Okay, so our first arm is actually pointing 0.265, which is nothing but our arm length, and y 0, g 0, and 1 should be there because I'm gonna plot this body in a 3D plot of the MATLAB, and I'm gonna multiply homogeneous matrix, which we will see soon after, that requires this fourth value. Okay, you can just put 1 there. Okay, and for the second arm here we define x as 0, y 0.265, z and 1 again. Let me just rearrange the values for your convenience. And once again, our arm number 3 is located here, and finally our arm number 4 should be located here, right? Easy. Okay, and I'll just put another body, let's say a payload. Okay, this is a center of our drone, 0, 0, 0, and I'm gonna add some body, I'll say a payload. Okay, like batteries or flight control computers or receivers or something like that, as okay, 0, 0 minus 0.15. Okay. So these are our initial parameters and constants, and actually we can also define some gains for our controller. Okay, actually we have to build a attitude controller and position controller and trajectory planner also to complete our project, right? In this project, you're required to fly your drone from this initial position to via this x1 and x2, right? So actually you need a proper trajectory planner also, right? But well, actually I'm gonna cover this attitude controller only because you know why? Because if I program everything, then it is not a project, right? So here I'm gonna state only PID gains for attitudes only. Okay, for example, this is a PID gain. This is PID gains for what? Pi angle, pi Euler angle, and let's see. I'll just copy and paste. Okay. We also require PID gains for theta and psi, right? What else? Actually, we're going to control the G dot, which is which is here. We also have to consider the T sigma, right? I'm gonna generate this T sigma value. Actually, it is coming from the position controller, but I'm gonna put it here to control our altitude, right? So yeah, these are the PID gains that we are going to use. And so far we don't know actually which values are correct for our drone. Okay, so I'm just gonna put zeros to all values right there. Okay, cool. Well, the reason why I put all these parameters like that and named as drone number one is because actually I'm gonna use this OOP, which is Object-Oriented Programming method in MATLAB. Okay, so I'm gonna build a class named as drone, so that you can utilize this basic kind of, sorry, I'm just gonna add a folder named library and save this drone into this folder. Okay, so inside of this library folder I place this drone.m, and here we have our drone class. Okay, so basically this drone class can be utilized with other parameters, other constants, other control gains, right? You can place multiple drones and then then do whatever you want, like reconnaissance missions or swarm missions, whatever. Okay, so that's why I'm gonna define our drone as class, and this class actually requires members and something called methods. Okay, members is kind of properties inside. This is nothing but a variables saved in this whole drone class. Okay, it's nothing but a data inside, and this method is nothing but a collection of functions. Okay, these functions are interacting with the properties inside. Okay, did I misspell something? Properties. Well, I guess it requires and, right? Yeah. Okay. For example, here you can place gravitational accelerations, your simulation time, delta t, okay, which is a step or final simulation time. Maybe your drone can have your own mass, arm lengths, and what else? Yeah, the I matrix. And we can also define our state variable, the state vector, and the change of the state vector, which is x dot, right? In this nonlinear dynamics, right? Yeah, I just define this x dot as dx because we cannot do the continuous simulation, right? And your control vector here, u. So this is nothing but a data inside of your drone, okay? And your methods, the function, collection of the functions will interact with these properties, okay? Or the outside world, like this main, okay? So you generate a drone in this main.m and then, well, call these functions, the method, inside of the drone to, you know, calculate the things. Okay, let's just specify our state vector, which is a position vector, velocity vector, and Euler angles, and what omega is are all defined in this state vector, right? So, for example, okay. Here, this is your state vector x, y, z, dx, dy, dz, Euler angles, pi, theta, psi, and p, q, r, right? Here, you have x, y, z only, okay? I just separated these vectors to, you know, to simplify our calculations later on, because for example, here your equations of motions are all separated in into, you know, velocity vectors, Euler angles, and angular rates, etc. Right? So I'm just gonna separate this chunk into 4 different vector. R, dr, Euler, and omegas. Okay, and this dx, let's leave it that way. And u also contains what? T in m, right? So actually your u consists of T sigma, M1, M2, and M3, right? So here T is just T, right? Your total thrust, T sum, and M indicates a vector consists of M1, M2, and M3, right? Right? Yeah. Okay. And well, these properties are all for this dynamics, okay, dynamics part. However, here I'm gonna place some other properties like desired pi angles and error of the pi angle, and some variable named as previous pi error, because we have to make a decontroller, right? And some for, you know, I controller. And I'll do the same for, obviously, like theta and psi, right? Oh, I missed the g dot, right? So these properties are just for, you know, controllers, right? So yeah, we need gains also, kp pi, ki pi, kd pi, kp theta. Let's just copy and paste them. It should be psi's, and here any g dots. Okay, I think this is all for the properties. Okay, and this is time to define some functions. Okay, for the drone. Okay. Actually, in the oriented programming, am I speaking right? Yeah, in object-oriented programming, you normally have a constructor. This is nothing but a initializer. Okay. So when you call this drone from this main.m side, then for example, like drone number 1, drone, then this will, you know, build your drone number 1. Okay, cool stuff, huh? And actually I require some inputs to this drone to build your, you know, your own drone with the with all these, you know, initial parameters, initial states, parameters and inputs, and all these gains, right? So this drone should contain parameters, initial states, initial inputs, and control gains, and right. And we can also define a simulation time. Okay. So if you build your drone number 1 by passing drone 1 params, drone 1 initial states, drone 1 initial inputs, and drone 1 gains, and then let's say the simulation time let's say 2 seconds for now. Okay, simulation time. So if you just pass these values, okay, to the drone, then this will make a drone. Okay, this will build a drone based on all these values. Now you can initialize all these values, okay, based on this arguments given from the main.m. But also you can do something like this actually. Well, this is some kind of values fixed to the environment, so I'll just type in the values. But for example, this final simulation time, you can use the values that just passed from the main.m, right? And we have the mass defined in this params as a map, as you can see here, right? We define the mass as 1.25, so this is nothing but a 1.25, and we can define our arm lengths and our drone takes ixx value and iyy and igz value, just like this. And I just constructed a I matrix, right? Okay, much easier to see, right? Okay. And what we have, yes, x. We initialize our state vector using initial states, right? And just let's just split our x state variable into right, r and dr, Euler and omega, right? So this is nothing but a object x from 1 to 3 is from 4 to 6. Euler angles are from 7, 8, 9 and 10 to 12. Good. And we don't know this dx for now, right? Because we haven't done our equations of motions yet, right? So I just put 12 zeros there, and u is coming from initial inputs, and I just split this u into t and m, right? I think this is pretty much it, right? Oh yes, we have errors also, right? Well, let me just copy and paste all these properties to our constructor here. Okay. And we should put obj dot in front of all variables. Okay. Well, this is nothing but a self dot in Python. Okay. It is highly recommended to initialize all variables, this properties inside. So here, well, let's just put all. Let's put zeros all the way to g.error sum. Okay, and this control gains are coming from gains here, gain arguments here, right? And this gain arguments is actually have this map here. Okay, so we define this gain as what, p pi, right? This is I, this is d, this is p theta. This is PID size, and finally PID z dot. Done, right? Yeah. Okay. And let's just run this main.m, okay, main, so that our drone is working fine or not, but it is not actually error in drone class C, line number 73, params mess. I guess this params mess does not exist. Or yeah, here I just placed this capital M there, right? So once again, well, I just run this main. Well, nothing comes out, which I guess we'll successfully build our drone number 1. Right? Okay. Let's get into the dirty works. Okay, so I'll just define a function called getState. Okay, actually you can access to the data directly, okay, from the outside of this drone, but it is not recommended. Okay, it is not recommended to do. It is something called encapsulation. Okay, you can Google for the object-oriented programming once again. Okay, this is some properties you can achieve. Actually, some features you can get from object-oriented programming. There are lots of good properties. Okay, so just Google them. Okay. I'm not going to explain this object-oriented programming. Okay, I'm actually not a profession. I don't have I'm not a professional to that. Okay, what I was about to do was like, building this kind of silly function, okay, so that you can indirectly access to this x states, okay, to access our states, okay. I just made this silly kind of looking function, okay, get state, because OOP is prohibiting, to accessing this your properties directly, okay. And another function we need to build is now our equation of motion, okay. Well, this will not return any values to the outside, okay. Yet this will update your dx here, okay, x dot actually, based on the equations of motions. Alright, so your dx1 to 3 is nothing but x values, okay, actually it's dr, right, which is, this is x values from 1, 2, 3, 4, 5, 6, okay. We just separated this x value into 4 different variables, right? And number 4 to 6 requires some equation here, you see, right? And b dot equals to mg blah blah blah. I'm just gonna replace this m to the right hand side, okay. So I'm gonna divide this m, and you have what, 0, 0 m times g, okay. Let me show you here again. This is mg part, okay. A3 is nothing but a 0, 0, 1 pointing downwards, okay, and plus rotation matrix all times your thrust, and 1, 0, 0, minus 1. This time your thrusts are pointing upwards, right? So based on our reference frame, which is pointing front right down, or NED, you should place minus 1 here, okay. Oh, by the way, we forgot to build our R matrix, okay. And this R matrix is actually converting any vectors in the inertial reference frame into what? Any vectors in the body fixed frame into inertial reference frame, right? So during the lecture, I explained how to build this R matrix, which transforms your any vectors in an inertial reference frame to the body fixed frame, okay. So this is nothing but a transpose of it. And what is BRI matrix then? I guess we need to define a function, okay. It's like roll PGO to rotation matrix. Let's call it like that, and it requires your Euler angles, right? So okay. What I'm actually looking at is, once again, this lecture note, okay. This is containing all the mathematical backgrounds behind of this program. Okay, so here, okay, I'm gonna build this, you know, R matrices into this function. Okay, RPY, roll PTO to rotation matrix. Okay, so it is returning R IB matrix. Let's say angles. So the first angle was what? Pi, right? Second was theta. The last one was psi, right? So R3, which is you know, we're gonna use this 3-to-1 conversion. Okay, 3-to-1 or GYX order to, you know, build our direction cosine matrix or rotation matrix. So we need what? Cosine psi, sine psi, 0 minus sine psi, cosine psi, 0, 0, 0, 1 for R3 matrix. And the second rotation matrix looks like cosine theta, 0 minus sine theta, 0, 1, 0, sine theta, sorry, 0, cosine theta. And finally, this R1 matrix should be 1, 0, 0, 0, cosine pi, sine pi, 0 minus sine pi, cosine pi. Then your rotation matrix from inertia to body is nothing but R3 times R2 times R1, right? Done. Okay, let's put it here, library. Okay, done. So now we defined our rotation matrix. Okay, so now let's get back to what rotational motions. So once again, here is your rotational motions, right? As I mentioned earlier, I really like to integrate these two, you know, equations above, but I'm gonna show you this Euler parameterization because you guys are all familiar with these methods. Okay, so before that we need pi and theta value to build this matrix here, right? So the equation should be object dot dx 7 to 9 should be 1, and sine pi multiplied by tangent theta cosine pi times tangent theta, and 0 cosine pi minus sine pi, 0 sine pi secant theta cosine pi secant seat. This is multiplied by what? This matrix multiplied by omega. Omega will give you the next time step. Actually, the change of Euler angles. Okay. And you also need angular accelerations, right? This is once again I'm gonna invert this I matrix, okay, to remove this I in front of this omega dot, so it will be like obj dot I backslash obj dot m minus cross product of your omega vector with I omega, right? Okay, I guess this is all for these for our translational motions and rotational motions. Okay, I just finished this equations of motion part, and now, well, actually we have to we can actually update our state based on this equations of motions. Okay, what I mean by update is like building another function, update state, like propagating to the next time step. Okay, so first you run this function to figure out the delta x, and then you can figure out the next state based on simply multiplying dx with dt. Okay, this is a very basic kind of integration, right? Method name Euler's method. Okay, so to get your next time step state vector, you just multiply your x dot with this dt. Okay, it's just a tiny bit time step. Okay, you can also use other methods such as RK4, which is Runge-Kutta fourth order methods, or something similar, other methods to increase the accuracy, okay, of your simulator. Actually, that is why I'm suggesting you guys to use a Simulink as the tool to complete this project, because you can choose whatever you want. Okay, I mean the integrators inside of the Simulink. Okay, but here we are just using MATLAB. Okay, so I just used this basic Euler integration method to propagate to the next state. So now you can also get the next step, RDL, Euler, and W based on this X. 1 to 3, 4 to 6, 7 to 9, 10 to 12, right? Okay, I guess we've done pretty much of it. Okay. Now I'm gonna build a basic kind of controller. I mean the innermost loop of our controller, the attitude controller. Okay. Well, it actually requires some reference signal, okay, from the outside. Well, okay, let me do this thing in this way, okay? I'll just go with the zeros. I mean, there's no controller, okay, for now. I think I should check if our dynamics works perfectly, okay? And then I guess we can move on to the controller part, okay? So I'm not gonna control the drone for now, but here control number 1 should be MG, okay, to balance your drone at the initial state, okay. I mean, without any kind of moments, your drone should be state input, okay, at this origin, the initial position, okay. So let's go back to our main and see if our drone is our drone dynamics is working perfectly or not. Okay, to do that I need to define some figures. Okay, I'm gonna plot two figures. One is 3D figure, the other would be a data figure. So I'm gonna put this first figure on the screen like 0, 200, 800, 800 maybe. Figure. Yeah, seems okay. And let's define a handle. And I'm gonna show it as a 3D figure, something like this. Actually, we have to flip the Z direction here. Okay, this is showing Z upwards, but we need Z downwards, right? So G direction should be reversed. Okay. Okay, cool. and it seems like this well, seems like we have to check if X label, right? We have to check whether this X, Y, Z axis are all pointing right directions. So something went wrong, right? X label. Oh, sorry. So this is our X, right, pointing north direction. I guess we also flip the Y axis, right? Okay, let's check it once again. Yeah, seems right. Okay, front, right, and down. Okay. Now let's make it axis equal grid on, and let's put some limits. Oops, sorry. Minus 5. Well, actually, we don't need above 0 because, you know, well, yes, because 0 is our ground. Okay, when G gets higher than 0, then the drone must be placed into the underground, right? Okay. Okay. So now I'm gonna draw our drone. Okay. As I mentioned earlier, we do not directly access to this drone's parameters inside. Okay, the properties inside. Later we call a function, okay, to protect our data inside. Okay, so drone 1 has this method called getState here. Okay, so if you call this function, then this getState method will spit out this data inside. Okay, all states, and we're gonna build a homogeneous transformation matrix. This is a 4x4 matrix, consists of rotation matrix, and its position along with 0, 0, 0, 1. Okay. So this homogeneous matrix is nothing but a R, which is a 3x3 matrix, contains your rotation. Let's say attitude, okay, and 1, right? Sorry, your position. your R matrix and your this is 3x3 matrix. Once again, this is your R matrix, okay? Your R matrix, and this is your small r, okay? So this contains position, okay? This R contains your attitude. Okay. Well, you can put 0, 0, 0, 1 at this final row of this homogeneous matrix to express this position and attitude of your drone, but this is nothing but a vectors containing perspective and global scale. Okay. So, well, you can just place 0, 0, 0, 1 at the last row, okay? So what I'm gonna do is like multiplying this homogeneous matrix, which will move our drone body into the world inertia frame. Okay, so here is our drone 1 body, okay, which is our drone defined on your body fixed frame, okay, your body fixed frame here, but now it should be expressed in what? Inertial reference frame with a certain attitude and position, right? So this homogeneous matrix will move your drone with a proper attitude, okay? So inside of this drone drone 1 and the word matrix, you can get this attitude from first to the third rows. Okay. Okay, for more information for the homogeneous matrix, well, you can always Google them, right? Quite a mess. So, for example, these values are all can be used in this 3D plot, something like this, something like this. So what I'm just typing in is like drawing a arm number 1 and 3 okay, inside this plot, okay. So this is actually connecting this is actually connecting these 2 points 1 and 3, okay. This is X position, and this is your Y position and your G position. Let's give some colors and the shape. Let's say 5. Here, for example, I want to connect the number 2 and 4, right? So here should be 2, 4, 2, 4, 2, 4. Let's put another color. And here, for the payload, we define the payload as line number 5 and 6, right? So if you connect these 2 points, then you will see a payload on top of your drone, okay. See, right? Oh, looks really cute. Oh, where are you going? Yeah, there. I just want to zoom in, but it's not working. Okay. Anyway, you can see a drone. Okay, sitting at what 0, 0, 0 with initial attitudes. Okay, and I'm gonna put something called a shadow here, okay, to express your drone's shadow, actually, okay. Maybe 3. Well, I just place this shadow because, for example, if you change this initial position, like maybe -6, then your drone will fly up there, right? You can see there. But here, sometimes you want to see this ground position of it, right? So I just place the shadow of it. Okay. Now I just hold, and for the data, well, if you are using a Simulink, you just plug in some kind of scope, okay, scope block to draw all these figures. Well, since we are using MATLAB, I should type in all these stupid things. Okay. Let's just. Well, I'm actually building 6 subplots. Okay. To plot your attitudes, like 3 Euler angles. pi, sorry, what? Theta, psi, and x, y, z positions. Let's put g dot here because actually we have to tune our control gains. Okay, then we need this pi, theta, psi attitudes and what g dot, right? Because we are about to control the g dot, not the g directly. So yes, let's put some grids and put hold down. Okay. And see if it's work fine. Okay. Let's just reduce some size. This. $500, 400, right? Oops. Yeah. Great. Well, then what we were about to do is actually actually checking if our simulation, actually the dynamics of our simulator works perfectly or not, right? So I'm gonna iterate this evaluations and state update to propagate our drone from our initial state. Okay. So our drone is not actually equipped with this attitude controller, but I'll just put this attitude controller for later. Okay, and you update state. Okay, so when your controller spit out some control inputs like thrusts and total thrust and M1, M2, M3 moments, then your drone can update its states based on all these forces. Okay, force and moments, and you just update the state, and this state can be seen from this get state function. Okay, and let's check if our drone is moving as we have intended. Okay, once again, this homogeneous matrix can be built upon sorry, this WHB homogeneous matrix, and you can get this attitudes, okay, by multiplying this homogeneous matrix. And now we can set, actually we can move our number 1, 3 into this new x value, or and this y and g values. Okay. And you just do the same for arm number 2, 4 and your payload and this shadow, right? Okay. For the shadow, we just require this x value of our drone. Where is it? Drone state. Yeah, drone state. We just require this CG position, right? X position. Y and G should be 0, right? Done. Let's check it. What is happening? What is happening? Maybe we need draw now. Uh-oh. Whoa. Wow. Don't forget to close all, okay. Yeah, see? Well, since we don't have any controls, right? We didn't put any controls. Uh-oh. We do have. Yeah, we do have, but we didn't update this signal into what? Our T, right? And M. Bum 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 2 2 3. What you have just seen is like it's a free fall of our drone, right? Uh-oh. Matrix dimension must agree. Yeah. Ah, sorry, 2 to 4. C. Yeah, so this is nothing but a free fur of our drone. Okay. Why don't you put this? Why don't we put this method like if our drone hits the ground, we just kill the simulator. State number 3 is greater than 0. Phew. Yeah, crashed. Right? Yeah. And now let's complete our figure number 2. Okay. Figure number 2 contains 6 different values. Ooh, sorry. Six different subplots, namely pi. One, two, three, 5, 6, 7. Step number 7. This is radian, right? As you know, it is not a fancy way to plot some data like this, because it will accumulate your data into the plot, which will slow down your simulation speed. But well, this is just a short tutorial for simulation building, so let's go with an easy way, okay? Yes. So your G dot is increasing, right? Looks like this slope is what, 9.8, right? Or more than that, not sure. I guess it is 9.8, right? And actually I simulated this for what, 2 seconds, but it is crashed, right? It crashed on the ground, so simulation just stopped. Okay, so I guess our dynamics is working fine. Okay, except this attitudes. Okay, so let's check that. Let's check that also. Okay, so for to ease our guess, I just put the mg to the total thrust. Okay, which is pretty obvious, right? Your drone should be hovering, right? Now let's change this U2 value a little bit, like 0.1. This is M1 moment, so your drone should roll right. Okay, is it doing roll motion or right? Yeah, see, yeah, now it's flipped. It is going to the right. Okay, and let's check the pitch. Okay. Yes, it is. It should pitch up, right? Which means your X position should be now negative. Yes. Great. All right. Now I'm gonna check this yaw moment M3. Okay, so I just put 0.1 there, so it should the drone should turn its heading to the right. Okay, let's check it. Size increasing, which means your drone should rotate clockwise. Yes, great. So what's left is like building a attitude controller, right? So if I complete this PID attitude controller, what you should do is like build this auto loop. Okay, where's the controller part? Okay, so I'm gonna show you today like an attitude controller along with this T sigma, the JITA control. Okay, and what you should do is actually feedback some sensor measurements like your positions. Okay, in this attitude controller, I'm gonna feedback this attitudes only, but you have to feedback what positions. Okay, and then you should spit out proper roll, pitch, and yaw commands. Okay, I'm gonna simulate these commands today. Okay, as zeros or 10, 10 or minus 10, whatever. But you should spit out proper values from the position controller, which is auto loop. Okay. And finally, actually, what you should have to do is build another thing called as trajectory planner. Okay, in the end, to complete your project, something like this. Okay. So, now let's begin the controller. Oh, actually this is our controller. So we don't require this U1 to U4 because it was just for the test. You get these reference signals from where in this main function. Before this for loop, I actually placed these numbers, right? T sigma G1. Oh, sorry. So this is angle. Degree, angles defined in degrees. Okay, so I'm gonna put D2R there. Good. This false reference signal is not embedded g.desired. Okay, so you now put a oh, actually g.desired must be coming from here, but yeah, like pi, theta, psi desired are all coming from this position controller, or now I'm just putting arbitrary numbers. Okay. And these desired values can make error signals, right? Based on your sensor measurements. And actually we didn't model our sensors, right? We are just using a clean state values here. If you want to add some noises or whatever, then you can just put random values or other models to, you know, simulate your sensors. Okay. Oh, sorry. Pi, theta, psi. Okay, so now you have error signals. Where's the controller design? Okay, so the for example here you can say this is a pi error. Okay, this is a pi error. Well, this is small angle approximations. Okay, and well, yeah, actually you can use pi dot or yeah, pi dot command and pi dot here, but for by using a small angle approximation, you can also use p command minus p here. Okay. Well, what I was about to do is building a controller, right? This is M1, right? M1. So you just multiply the P gain and with this error, okay? And I guess you guys are already typed in this error sum and error previous values, right? Well, this is actually for, you know, integration and differentiation. I'll explain them later. This is error minus pi error previous divided by object. Right. So here I'm just accumulating these errors, okay, to build our I controller. Okay, actually it should be integration, but we are using what microprocessors, for example, such as DSP, digital signal processor, or ARM, okay, to control our drones in real life. So we differentiate error by using df over dt, which is not very recommended because it sometimes gets unstable with sensor noises and highly depends on the time step or computing powers. And you accumulate errors in a discrete way as a substitute for continuous integration. Now we just copy and paste them to complete theta and psi controls by changing their names. Sorry, I haven't noticed there's some audio problem. Okay, now I'm back. Okay, so finally we define this G dot controller. Okay, also PID. Okay. Right. TM done. Okay. So let's play with this U2, which is M1 first. Okay. Let's move it to 10 degrees. Okay. O. Okay. P pi unrecognized message. It is all lowercase k. Sorry. And by the way, actually differentiation is not recommended in digital signal processors. I mean the microprocessors, and not just microprocessors like discrete time analysis. So what we do in normal life is kind of multiplying this 0 minus obj dot omega 1, which is what the p value. Okay, you can actually measure the angular rates of your drone, right? So this is coming from your sensor. Then 0 is like pi error signal dot. So if you are planning to build a attitude controller, well, the derivative of it is normally 0, right? But in many cases, well, it has certain value, right? If you have a proper trajectory planner or auto loop, like a position controller, then yeah, you might have one. But for now, I'll just put 0 here, okay? Because what we are going to do is nothing but putting an arbitrary number in it, okay? Well, just for now, we're gonna use this derivative, okay? So let's check it. Oh, what? KD pi is not recognized. Well, sum is uppercase sum. Well, sorry for that. Still. KP, KD, 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 KD. All right. Okay. Yeah. Why? Oh, okay. So actually, we didn't put any PID values where. Here, right? We don't have any gains for the controller, so that was the problem. And before we do that, let's just say obj.u1 should be mg. Okay, I don't want my drone goes down to the ground while I'm tuning these values. Okay. Well, actually, we can tune the G dot first. Sorry for that. Let's first start with this pi first. Okay. Yeah, it is moving. And seems like it is oscillating, or yeah, it is oscillating. So what you can do is like decrease the gain or decrease the P gain. Well, how should I stop it? Right. Well, what we can do is like decrease the P gain, okay, like 0.2 maybe, and see the response. well, still it seems like overshooting or oscillating. What you can do for now is like what, increase the D gain to, you know, reduce this overshoot or something. Looks much better.
Welcome to VoiceOver. VoiceOver speaks description.
Sorry for that. Maybe 1.5. Even better. Well, actually, this is not a tutorial for how to tune the PID, right? So I'll just move on. So basically, this drone has symmetry, right? So I'm gonna copy and paste this value to theta also. And psi, well actually it has what, it has doubled moment of inertias, and then I'll just double the values, okay? And let's check whether our attitude control works nicely. Yep. Well, it goes somewhere, right? All right. Well, anyway, it is, you know, it tries to converge to 10 degrees and psi to 30 degrees, right? Well, fine tuning is your works to do, and I'll just show you how this G dot controller works. Okay. Let me just remove this and give some value here, like 1 meter per second of altitude decreasing. Let's pick 1 maybe. And all right, for now I'll just kill the controls from 2 to 3, okay, 2 to 4. That's 0, 0, 0. Okay. Ooh. Seems like it does not work. I placed the G dot as 1, but it is keep, decreasing the altitude. Oh yeah, actually for this G dot control, we normally put mg. We just compensate these gravitational accelerations, and what this minus sign indicates is what, indicates that your G is pointing downward, right? G positive is pointing downward, so this value is positive when G command is higher than G dot, right? So yeah, you do the math. You can do the math, right? So well, without this minus sign, your PID values should be all negative, right? Due to these G values are actually pointing downward when it is positive, okay? So this is why I placed a negative sign before this bracket. Okay, and this mg for compensation, gravity compensation, and this error. Yeah, I'm sorry. This mg must be obj.m, obj.g. Still not working. Could you stop? Oh, I've made a big mistake, right? I didn't define g.error in the first place. It is dr number 3. Right. Now it should work. Yeah. Seems like the gain is too small. Yeah, too small. Maybe 10. Yeah, much better. Cool. Yeah. Right, then now let's check all controllers. Let's just check the all controllers are working as I intended. Yep. Right, they're doing great. Cool. Well, I think there's some, steady state error between this one and maybe you can put some values here to, decrease this error. Well, it looks kind of decreasing, but I'm not sure. variable go to this exactly, whether it will converge to 1 or not. Well, still, well, well, actually, this is not my job to do the fine-tuning, okay? So what's left is like fine-tuning of PID controller. Controller gains, and sorry, I'm gonna, yeah, and you should definitely build a auto loop, which is a position controller. Well, you should also design what trajectory planner, okay, to finish your project. And oh yeah, actually I haven't considered any motor saturations. I mean, for example, you have to define a function named as clip, which will return maximum value between your input and lower value, and then minimum value of what between this and upper value. I'm just save it to the library. Okay. So what this function will do is like in the problem set, you can see this condition: your motor cannot exceed 10,000 RPM. So in this, tutorial, I haven't considered any aerodynamic considerations. Okay, so basically what I have done is like building this T sigma to M3 from your PID controller. Okay, so what you have to do from now on is like consider all the aerodynamic forces, and you can figure out the proper KT and KQ values, right? And then you just do the maths and figure out the rotational speed of your motor. And if your motor does not meet this criteria, like 10,000 RPM maximum rotation speed, I mean, if your motor exceeds this RPM, then what you have to do is like clip the value and redo the maths. Okay, substitute the proper value there, and then figure out the proper T sigma, M1, M2, M3 values. Okay. So, yes. So I think I have done pretty much of it. Okay. Alright, so good luck on your final project, and Merry Christmas, and also Happy New Year. Thank you.